welcome back everyone. I'm going to talk now about how we model the terrestrial biosphere, at least in general terms. And I'll make you a deal about the last half of the lecture. We're going to talk about the model we're going to use this afternoon in the pracs. So if you need a nap, try not to take it then. All right, let's have a look at an outline for this. Not going to get too philosophical, but it's worth talking a bit about what we mean by a model. You've already seen models this week, and this is going to be slightly shaped by the fact that most of the time I do something that's in between physical sciences and statistics, trying to infer the way models behave. And then you run into all sorts of problems of nomenclature about what people mean when they say model. So we'll just kind of clear that up a bit. Talk a bit about theories versus models and what some of the gaps there might be. And this is really just background. A lot of you will have this, but I think it's important to think about what the difficulties might be for constructing particular kinds of models. Then talk about some general principles that models should or have to obey. Some kind of basic concepts in modeling, some common analogues or mathematical approaches that we frequently use to describe a system. And then the section where you need to wake up is talking about the optic model, which is a very simple biosphere model, kind of analogous to the box model you were looking at in the ocean early on, that we'll use this afternoon in a prac. So what is a model? Well, what do I mean by models? Perhaps a better way of putting that. So it's a quantitative description. There are qualitative models, but they're not what we're talking about here. It's a quantitative description of a physical system. And we're used to the idea of writing down models as equations. And then we implement those equations in a computer if we want to solve them. But that's not necessarily the way things really happen these days. If you look at any complicated computer model, you'd be hard-pressed to take that piece of code and turn it back into mathematics that describes the system. So we really do need to think about a kind of parallel description of a model where our knowledge of the system is instantiated or embodied as a piece of computer code rather than a piece of mathematics. The way we think about this is that when we change a constant in the model, we change a parameter. We don't change the model. But often that's not what a statistician means. They'll think of the model as being a particular parameter set as well. So a particular set of constants in the model, and they'll be trying to refine or choose the best model among those sets of parameter sets. So that can cause some confusion. But here we kind of think we know what we mean. Models don't have to be deterministic. There's no rule that says we run the model twice, we should get the same answer. That's not just because we're bad programmers. There really are models that are statistically forced, and the one we'll deal with this afternoon actually will be. So we often carry equations for the variance of the quantity, for how much it's going to vary around a mean, without necessarily calculating an actual realization for the thing. So if you say that the standard deviation of such and such on a given day is larger or smaller, and you ask what was the answer on a particular day, you might have an exact model for that thing. You might be making a random number generator to do it. And this all sounds pretty general, but it kind of matters when you come to actually write down a model. And there's a range of different classes of models. The most common difference, and this is really germane to the terrestrial biosphere, are between prognostic models, where we try and model how a system evolves in time. So we write down an equation that says if we know the state today, we can learn the state tomorrow as a function of the state today plus some equations and some forcing terms and so on. And that's so usually first order differential equations, and that's kind of the dominant paradigm. But often in the terrestrial biosphere, there's a class of models where we know what happened. We have measurements of what happened. We can look down on the forest canopy and see how many leaves there were. We've got measurements of what the flux of water or carbon dioxide or something through the leaves actually was. And what we're interested in is in diagnosing why that happened. And those models are usually called diagnostic models. And if anything, they probably dominate the terrestrial biosphere community. They're becoming less and less common now for reasons we'll discuss tomorrow, because a major use for the terrestrial biosphere models is forecasting, climate forecasting. It's pretty hard to forecast what the measurements you need to drive your models would have been in 2100. So you're kind of forced to use prognostic models. So there's a little more of a trend towards prognostic models, but it's still true that a very large number of models that are attached to current research efforts are deliberately chosen to be diagnostic because they're probably more accurate. You don't have to make a prediction. There's also another distinction that doesn't play so heavily in the terrestrial biosphere, is that what you'd like to do is learn what the fundamental equation, this is the physicist approach to a system, right? You'd learn what the fundamental equations are, and you'd write them down, and you'd solve them as best you can. And you couldn't necessarily solve them exactly because there might be problems of resolution and so on, we'll get to in a minute, but you'd solve these exact well-known equations as well as you possibly could. In a lot of natural systems, particularly ones that are subject to things like evolution, where the system is tweaking itself continually to optimize something or other, it's survival usually, it doesn't work. So you can't necessarily construct a perfect model of how plants behave. There's a really surprising amount that we don't know, and that would have been very clear as well from Alex's lecture yesterday, that we don't know a lot about how biospheric systems actually behave. And so we can't start from fundamental physical or chemical principles at the moment and generate a biosphere model. So we either proceed by kind of making analogies, it's like this, or by establishing kind of simple heuristic or simple empirical relationships between some measurements and some process that we think is going on, and then generalizing that relationship. And that's a really common, that's kind of the dominant form for terrestrial biosphere models, because we just don't know a clean, complete underlying theory. As a refugee physicist, I still find this frustrating. It's worth saying, though, that even if we did have perfect theory, it doesn't mean we have a perfect model. So we have perfect theory for the atmosphere. We know absolutely precisely the physical equations for fluid flow in the atmosphere. Does this mean that atmospheric models are perfect? No. And here's a very simple explanation about why. You have some prognostic model that says that the rate of change of Z with respect to T is equal to a product of two things. And you've got the two things measured, so that model is perfect at a point. No problem. But you're running this on a finite resolution computer, finite size computer, so you're not actually trying to estimate this at a point, you're trying to estimate it over some region, like grid box. So you then are forced to say, you've got all these variables defined on the grid box, and then you're forced to say, okay, it's still true, we still assume that the partial of Z with respect to T is equal to this product, but it's now the average of the product. And the average of the product is not the product of the average, as we show here. And so you're forced to make some guesses about how these two quantities vary on smaller scales than the grid box. So, and there's usually not such a clean theory for that. So even when you know precisely what the theory should be, it's very common that you can't estimate the quantities at the resolution that you can model them. That's bad in the atmosphere. It's particularly annoying in the atmosphere, of course, because we do know that what the equation should be, and we in principle should be able to model the processes exactly. In the biosphere, these two previous problems combine. So you can show, and there's been a lot of work about this, that taking measurements that you make at a point, say measuring the flux of something and what it's driven by, and then upscaling that, as I mentioned in the previous lecture, the very first problem you have is that you can't easily know what variables you should be upscaling it with. because it's often more than one thing and you need to know how they vary together. And so it's proven to be very hard in the terrestrial biosphere to establish relationships in the lab or at even a single point in the field that you can then take and apply to the kinds of regions, the kind of resolutions that you'd like in a global climate model. And this so-called scale problem, there was an explosion of papers around this area in the 1990s, things like estimating fluxes and stuff, but it turns out it permeates right through the terrestrial biosphere modeling. So even if we had perfect knowledge of what the relationship should be at a point, we couldn't extrapolate that to larger regions. Also worth mentioning a couple of words on chaos, since everyone likes talking about chaos. The previous case that I mentioned, people think of this as having something to do with chaos. It doesn't really. That's just a problem of the finitude of resolution. Chaos happens from the fundamental equations itself, where you can make a small change in input and get a pretty large change in the output. And with luck, some of the exercises this afternoon will show you that some quite simple models for the terrestrial biosphere can actually turn out to be chaotic. They can be quite sensitive to small variations in the initial conditions. Now, in general, the large-scale terrestrial biosphere doesn't seem to do this, but there is evidence that various natural systems will respond in ways that can flip from one regime to another. So there's some at least pretty solid theoretical and even observational work that the boundaries between, say, rainforest and savanna in Australia are controlled by fire, which is in turn controlled by the presence or absence of rainforests. So you get some disturbance event like a chainsaw or a cyclone, opens a gap. That gap means that fire is more likely, and that fire means that the forest won't regrow. You have another state of the world, a sort of counterfactual world, where the chainsaw or the cyclone didn't happen, and the forest goes on fine. And that kind of sensitivity is an example of something that we generally think of as chaos. There's also, in most models, a bunch of basic rules that we have to follow. You know, it's kind of useful if a model conserves mass. If we're trying to write down something like a carbon budget, we'd rather not lose too many of the carbon atoms, thanks. It turns out to be surprisingly difficult to do in a complicated model, or at least to get a mass conservation that has enough of the processes involved to mimic the real world. So mass and energy is doable, not straightforward, but there are a whole range of more esoteric quantities that models also need to conserve. That's more of a problem for fluid flow models than for us, because there aren't that many conserved quantities. Mass and energy are the two things we normally have to worry about. But as anyone who's looked at things like flux measurements will confirm, it's quite hard, even in a set of measurements, to make them close the energy budget for how much energy is coming into and going out of the surface. It's fine for the planet, as Robin was showing before, although it's pretty hard to make a measurement that shows how the energy budget is closed for the planet. But it's very hard to do this at a point. It's also surprisingly common to abandon it, to say that, well, I'd rather make a good weather forecast than conserve mass. It concerns me somewhat. But many of the numerical schemes that you see in very fancy weather prediction models don't conserve mass. They don't need to, because they're only running for such a short time that we'll reinitialize the model tomorrow and fix it. Doesn't matter. But for the kinds of models we're using and the kind of timescale that we care about, we do have to worry about this. Almost through the taxonomy. Finally, there's a bit of a question about what you want to use a model for. And the common split here is people who just want to use a model for some utilitarian purpose, like a prediction, weather predictions, the CAISIC. And you don't necessarily need to understand a weather prediction model. In fact, they're really hard to understand. There's my PhD supervisor was fond of telling me they're as hard to understand as the real system. If they weren't, there wouldn't be decent analogs for the real system. So the only advantage of a computer model over the real system is you can break it without getting into trouble. So you don't necessarily need to understand a model if you want to use it for prediction. It pays. You're probably going to, in the end, make a better prediction. But lots of people in places like numerical weather prediction centers are making changes and saying it improved the forecast. Don't really know why, but that's my job, and I'm quite happy about that. Now, I don't exactly know why it's not quite fair. They'll have some ideas, but they won't necessarily bother to try and drill down to how does this fit the fundamental theory or whatever. The advantage is that they get to test these models really frequently. So they get to test it. The numerical weather prediction person gets to test their forecast several times a day if that's the forecast cycle they're running. And to be fair, there's a great deal of research that tries to use the fundamental theory to improve the weather forecast. But I can tell you from experience, if you come up with a scheme that says this is more in accord with the fundamental theory, and you implement it and it makes the forecast worse, it's not going to get used. Because that's not their job. If you're running a research model, your tasks are a bit different. As I said, you're allowed to break it. It's a numerical laboratory. So you can see what happens if in an oceanography experiment, if someone happens to remove the Australian continent. It's hard to get ethics approval for doing that on the planet. But you're perfectly free to do whatever it takes to understand how the model works. Usually, you run the kinds of things we were seeing before. You try and analyze your complicated model in terms of a simpler diagnostic model. So the same kind of diagnostic models that you'll apply to the real world in general, and you try and see whether the simple model gives you some understanding of the way the complicated model is behaving. So it's called a model hierarchy. It's a really dominant research methodology in the earth sciences in general, that people have a full-on model that they use to say, yep, that looks like the real world, so we can take it apart and see what makes it tick, and we hope that the same mechanisms will apply in the real world. And that's not generally what you do in a forecast calculation, for a forecast model. You'd be most interested in, does it help? And these diagnostics, you're always fighting the temptation to make them too simple, so you can get them on a nice single graphic and understand them well. So Einstein's famous quote about the truth should be made as simple as possible but no simpler holds very much for trying to understand one of these models diagnostically. The conclusion of that philosophical ramble is that there isn't the best model. Models have a domain where you want to use them. And it helps if the phenomenon that you're analyzing with the model, hopefully a real world phenomenon, is well simulated by that model. So it's pertinent to its domain. For a research model, you kind of need to explain it either directly by glaring at the equations or by using these simpler models. And I've made a comment here on data assimilation, which is not particularly relevant here, but the key test there is can you simulate the data? And if you're going to try and infer how the model is behaving, that's always the first test that you need to do. Now down to some details for what we actually care about in models of things like the terrestrial biosphere. And the key concepts here, which I suspect you've already dealt with earlier in the week, are to do with stores, fluxes, and residence times. So the classic equation for this is that the partial of the derivative of some stock, some amount of stuff with respect to time is proportional, is equal to the flux in minus the flux out. And that's just conservation of mass. You can also write that as a concentration if you want to carry a mass of the underlying reservoir there. But either way, those are just different versions of the same thing. The change in stuff is equal to flux in minus flux out. That's not very hard. And it's a prognostic equation for the quantity. That's great. Now, a very common form in the terrestrial biosphere for the outgoing flux from a box is to say that the outgoing flux is proportional to the amount of stuff in there. So we might assume that you've got a bunch of microbes eating carbon in the soil and turning it back into carbon dioxide that goes back into the atmosphere. And the assumption you'd make is if you double the amount of carbon, that you'll probably double that flux. And that assumption turns out to be questioned in various cases, but that's the general assumption that we'd make, that the flux out of most of these boxes is some rate constant times the amount in there. That leads you to a useful but problematic concept called the residence time. So we write here that, again, the partial of Q with respect to T is equal to minus KQ. And then you can write a kind of first order time stepping equation for that beast that says that at T plus delta T, it's equal to Q at T minus K times Q times delta T. Easy enough to do. And then you say that you extrapolate that equation and say that at time T is equal to 1 on K, Q will be 0. The box will be empty. And so that's canonically called the residence time, because it's the time that all the stuff in the box will leave. Now, of course, it doesn't happen like that. Probably enough of us have done enough calculus to see that that would actually be an exponential solution, because, of course, as the box gets depleted, the rate of depletion changes as well. So what actually happened, but for a kind of general shorthand, that residence time is a very, very common thing to quote. There's a real catch with residence times, which I've commented on here. And the best way of talking about this is actually to cite an example, which I don't think I wrote down, but there was a pretty strong push in the climate skeptical community, I prefer to call them climate naysaying community, who don't think climate change is a serious problem. Around the end of the 1990s, it said, if we turn off fossil emissions today, CO2 in the atmosphere would return to its pre-industrial value in 7 years. And those of us who are used to dealing with these numbers said, that's got to be wrong. How on earth did they come up with that? So the way they did this was to say that at that stage, there was about 700 petagrams of carbon in the atmosphere. And there was about 100 petagrams of photosynthesis happening every year. So 100 petagrams is a flux. So you can divide the store by the flux and get the residence time, and it's about 7 years. So people actually said, and you know, this certainly turned up in testimony to the US Congress, that it's a 7-year problem. We don't need to worry at all about fixing this. It'll go away. Can anyone see the problem? Most of it comes back. What you've done is chosen to write down the budget for the residence time with respect to just one process. That's valid. It's a valid comment on what the residence time is with respect to that process, but it's not a valid comment on the residence time of material in that box. To do that, you've got to look at the total flux. So you can't write, you should never be writing a residence time down of a quantity. You should always be writing it down with respect to some particular process. One more piece of background that we need before delving into how some of the models actually work. And I wasn't there for one of the lectures earlier in the week. Did we see Michaelis-Menten kinetics? Yes. Good. In that case, I can relax about this. Michaelis-Menten kinetics are because they're kind of based on how enzymes behave, really dominant, and they turn up all over the terrestrial biosphere models just as much as they do in the ocean. So you see that familiar, hopefully, form, that is kind of asymptotic approach to some maximum rate, and you get to set as parameters both the maximum rate and how much stuff will get you halfway there. And these turn up just all over the place. All right, now a modeler's view of the biosphere. And this will kind of now troll through this in a little bit of detail to see how some of these terms work. So the general idea is that you have what's called gross primary productivity. Again, you've probably seen most of these terms in the ocean. That comes down, that's roughly photosynthesis. There's a bit of terminological care required there. And that tells you how much carbon is being taken up by leaves, by plants. A lot of it doesn't stay there. It's re-respired by the plant in order to survive. And, but what's left is called net primary productivity, and it's essentially the growth in the plant. Those plants will die either seasonally or on longer terms, and that carbon will generally pass to the soil where it's kind of dealt with by animals, microbes, whatever, and is eventually returned to the atmosphere. Some of the models don't try and deal with GPP because it's yucky and biochemical. So they'll start with a description just for, can we describe a simple model that tells you how quickly plants will grow under given conditions? And so the rest of this lecture, the next few minutes, is going to be defining various of how the fluxes in those in that cartoon are modeled. And we start off with the one we know most about, and this is a decidedly complicated cartoon of how photosynthesis works. But the key point is that photosynthesis is a combination of photons and CO2 and water, and that you kind of need both. So there's a mutual limitation between the amount of light that can be absorbed by the chlorophyll complexes in the plant and the amount of CO2 that they can fix. And the amount of CO2 they can fix is often limited by how much they can get in from the outside, because they'll deplete the stores of CO2 in their leaves fairly quickly. And that in turn is a decision that a plant has to make about how much water it's prepared to give up in many environments. So there's a series of strategies, if you like, to make sure that plants have as much CO2 as they need while not risking a range of other damage that can emerge from usually from losing too much water. So the key point is there are these two processes, the fixation of CO2 and the absorption and transport of energy in the form of electrons, and that those two processes define two maxima for this rate. Autotrophic respiration is what plants need to stay alive and to grow. And both those cost energy, and that energy is usually used by kind of, as with the process that Alex was describing yesterday about feeding useful passengers, symbiotes, to provide you with nutrients. There's an allocation of, actually I'd be interested to know whether that's usually included in autotrophic respiration. But there's photosynthate that's dedicated to the task of just staying alive and growing for a plant. And you have to model it. You have to decide whether there's some simple relation that you can write down for autotrophic respiration as a function of, say, how fast the plant is growing or how much stuff, how much it's actually absorbing. And then you come up with an expression that says that the growth rate of the plant is equal to how much is coming in, GPP, minus the autotrophic respiration. As I mentioned earlier, a lot of people start there. So instead of trying to estimate the photosynthesis and the autotrophic respiration as explicit mechanisms, they start with a model that says that the plant growth is proportional to something else times an efficiency factor. And the something else might be how much light is being absorbed on these leaves, or it might be how much water is being transpired by these leaves. It usually depends on something else you can measure. And these are usually diagnostic models. So a lot of the models are satellite driven because they can measure using measurements of reflectance how much light in the key wavelengths is being absorbed by the plants, and that they can then use some transfer function to turn that into plant growth. And that's these so-called light use efficiency models really completely dominated the field for a long time. Some other places use water use efficiency models, same functional form, but where you have some expression that can tell you how much water is being passed through the leaves of the plant. That is commonly used in models that are coupled into climate models, because they need to estimate how much water is being passed through the leaves anyway, and they can use that in a fairly simple form to generate a plant growth. Now, the original equations here were actually derived for GPP, photosynthesis, because they generally thought about how much stuff is happening at the leaf level, but it's been believed and sort of observed for a long time that GPP and NPP are pretty strongly related. So you can transfer this to a model of actual plant growth. Now you know how much the plant is growing by one means or another. You have to allocate it. And the models here vary a lot in complexity. So a lot of models just say anything above ground is a leaf. You might look out at a tree and think that's probably not quite correct, but that's what a lot of the models do. Things are either leaves or they're just stuff to support leaves. And it's often called a live biomass term. More complex models will carry several types of carbon in the living biomass. So they'll have leaves, they'll have stems, and they'll have roots. And they have to decide, so to plants, how much of their fixed carbon they're going to allocate to each of these boxes. And usually in a model, those are just fixed numbers. We have so-called allocation coefficients that tell you that 20% of the carbon that comes in is going to be sent to whatever, 40% here and the other 40% there. And adaptive strategies that plants might undertake, which they certainly do, to change those allocations with various needs, are actually, in the kind of global models, are not particularly common until they're turned out to be needed. So people have discovered that plants respond to various trees respond to drought by making bigger roots to get to the water, surprise, surprise. And so in order to simulate how the biosphere reacts to a drought, that effect had to go into a model. So usually you'll add a complexity to a model like that only when you find out that your simple model doesn't work anymore. So some of these models are now starting to deal with allocation in a more sensible way. Lastly, you've got to deal with what happens to the biomass after it leaves the plant. So leaves have a finite life, varies a great deal with the environment. In the Northern Hemisphere, it tends to be, for obviously deciduous trees, it's pretty short, lasts a season. Conifers, it's different, or needle-leaf trees, it's different. And broadleaf evergreen trees in the tropics and places like Australia, it's different as well. We really don't model this very well. In models that I know best, there's either the leaves just fall off and it gets cold, or there's a leaf age that just tells you how long the average leaf is going to live. And it's a single global parameter. Every tree does things the same way, right? And we know that's not true. But you have to trade off just how much complexity you're prepared to live with. And that's a residence time for leaves. It's a residence time for carbon in that leaf biomass pool. There's a pretty distinctly Northern Hemisphere bias to the look of this. There's quite a complex treatment in the models about when it's time for the leaves to die. When does so-called senescence set in and the leaves give up fixing carbon and change color and fall off. And there are temperature-based rules and so on how to do that. The rest is handled by a single parameter. It tells you how long the leaf is going to live on average. And it's clear that's wrong. But it's really quite, you can often tell, if you look at a terrestrial biosphere model and compare it with observations, you really can frequently tell where it was written. Because it almost always compares best with measurements in its backyard. It's quite a strong motivation for places like Australia to be developing their own models, because the Northern Hemisphere ones just don't work very well. Finally, soil carbon. Again, it's often divided into fast and slow pools, or occasionally more fancy continuous descriptions. And that's a case where, again, you have a residence time, you have a constant that says that some fraction of the carbon is going to be respired back to the atmosphere or transferred to the other compartment in each time step. The constant, and this is often a function of soil moisture and temperature. And that's one of the places where, in tomorrow's lecture, we'll see that the climate can drive the response of the overall biosphere, because some of these constants are functions of temperature and soil moisture. Change them, and you can change the respiration. And indeed, in the models, it happens. That's the tour. It's worth thinking about the summary statistics for this stuff. So how big are these fluxes in general? This is from a model, because for many of these things we can't measure them directly, but the model's being tested against a range of observations. Got to say, it's been tested. It doesn't mean it passed all the tests, but it didn't do too badly. So in general, the GPP, the amount of photosynthesis, is thought to be in the range 120 to 130 petagrams of carbon per year. That's a lot. So remember that the fossil fuel flux is about, these days, is about 9 to 10. So photosynthesis is much larger than that. That's why you'll see CO2 go down in the Northern Hemisphere each year, because this photosynthesis is so strong. About half of that, we think, stays in plants. That ratio is quite poorly determined, actually. It's kind of a rule of thumb, but it's very poorly known. And of course, then that has to balance overall, apart from the uptake, what's going into the biosphere. So you have about 50 or 60 odd petagrams of carbon being fixed in plant growth, about the same amount. The biosphere isn't changing in size that much. About the same amount comes out each year. And about 2 petagrams of that is stored in the soil. And that 2 petagrams, that looks like magic, because that just happens to fit with the numbers that you saw from the global carbon budget earlier. It's not magic at all. It's because we made it do it. The model was constrained with observations, and that's what comes out when you do that. So if you don't do that, the actual residual sink, if you think about how hard that problem is, you've got 130 petagrams of carbon coming in. You want to try and estimate how much of that stays in the soil to about 2%. It's actually quite a hard task. Okay, my summary of terrestrial biosphere models is that they're unsatisfyingly complicated. But that might be our fault. It might be that nature's just like that. Evolution has had a long time to come up with a lot of tricks for dealing with this stuff. There's an awful lot of empirical parameters because we don't have a clean underlying theory. There possibly isn't a clean underlying theory. There are relatively few fundamental constraints. It's possible that, and it's been discussed a bit in modeling, that evolution is actually, fitness is actually a fundamental constraint that we're not exploring very well. That there's a range of models arising now that deal with the fact that plants should be optimizing something. And that they've got to be doing pretty well at it, or they wouldn't be there. So there's some new approaches for some of these constraints that we haven't really used yet. Now to wake up. I'm going to discuss optic for the last 10 odd minutes of the lecture, and optic's the model we're going to use this afternoon. And it was motivated really by an attempt to do a comparison of parameter estimation methods for these models. So an industry had grown up where, because we couldn't write a clean fundamental theory for these models to know what these parameters should be, these allocation fractions and, that we try and derive them by comparing the models with data. The models are complicated, and so those attempts to infer them are relatively hard. And not many groups could do it, partly because the models were many thousands of lines and you had to do horrible things to them to make this happen. So we decided to come up with a model that we could get on one page that people could use to test their methods to infer parameters for these things. But it should be complicated enough that it looked like real biogeochemical models. If you like, it's one of these simple models in the model hierarchy. It had to be computationally very simple, so it could be very fast, because some of these methods involve running the model hundreds of thousands of times, and if the model takes 4 days to run, that's a bit of a problem. And it had to have enough of the kind of regimes, enough of non-linearity and so on to be interesting. And we couldn't define interesting very well, but had to make pretty plots was kind of the driver that we actually used. And there's a couple of papers here where we used the model to test various data assimilation schemes, and kind of, for fun and profit, really, had a good look at the dynamics of the model. I said it could fit on a page. There it is. So what we see is we have the models divided into two components. We have a live biomass component, X1, and a dead biomass component, X2, soil carbon if you like, and that the growth of X1 is equal to some term that actually looks like Michaelis-Menten kinetics. But it's slightly more complicated because it involves both X1 and X2. And the idea there is that soil carbon is going to be correlated with soil nutrients. We know that the plants need nutrients to do photosynthesis, so we can assume that nutrient availability should somehow be coupled to this other store X2. So we did some kind of a Michaelis-Menten product thing on X1 and X2, and that introduces its own set of parameters. Then we write a simple first-order decay term. So we decide that the amount of biomass that's being transferred from our living biomass term to our dead biomass term is proportional to the amount of living biomass. And finally, and we'll get to this in a minute, we had to add an extra term, a so-called seed production term. And we'll see this afternoon why we needed that. It's quite an interesting story. For the soil carbon pool, life's very simple. And it's an interesting story, by the way, that if you actually look at the lines of code in the terrestrial biosphere model dedicated to the various processes, you'll find several hundred lines dedicated to photosynthesis and 4 dedicated to soil carbon or something like that. This equation looks like that. It says that the fate of carbon once it's fallen off the live biomass is really pretty simple. You have an input from the live biomass pool and an output that's just proportional to the amount of soil carbon you've actually got. And there is a forcing term that drives the production in the X1 equation, in the living biomass equation, and that forcing is just how good conditions are for the plant. So the model was written in Australia by Mike Raupak of blessed memory, and so we thought of the forcing as rainfall. If it was Northern Hemisphere, we'd think of it as light. You know, it's whatever the plant needs most desperately. And it's random to a degree. So it is a kind of random forcing on this model. Now, I think I've described these equations roughly already. Find my text here. Yeah, so the first term, as I said, is a product of 2 Michaelis-Menten terms. And it means that the growth rate is going to increase the more leaves you have. So the bigger X1 is, the more leaves you've got to fix light. And so the happier you'll be, the more you'll grow. And of the substrate, the soil carbon, as well, because it's providing nutrients. So that's a defensible form for an equation like this. And the second term, as I said, is just a linear decay. Second equation, as I've already said, is much simpler. It's just an inflow into the litter, if you like, and an outflow as a first order decay term. So that really is optic. Those 2 equations are going to form the basis for this afternoon's prac. And kind of a rough summary here of, I think I've tried to make it clear that model is a rather fluid term. It means a whole range of different things. You should be careful when using them that you're using the right model for the right purpose. And that doesn't necessarily mean going to the most complicated model you can. It might, but it doesn't always do that. You will, however, though, if you do use a simple model, and again, quoting a personal experience here, we used quite a simple model in an early study of trying to infer these parameters, and we got 2 reviews back, and one said, this model looks like a PhD student's warm-up exercise, and the other one said, this isn't even a model. So just beware that if you do use a simple model, you're going to have to justify that it actually can deal with this. Unfortunately, we're not doing applied maths, so you're going to have to justify that it can simulate well enough the quantities that you're actually trying to deal with, so that the understanding you get has some application to the real world. For beyond that, there really aren't many kind of constraints, common forms for what terrestrial models should look like, except for the fact that some of these basics like enzyme catalysis and so on, and thermodynamics are pretty common. They're everywhere. And the last point I'd make is that I hope we can demonstrate this afternoon that you can construct hopefully interesting models, or at least models with interesting dynamics, from really quite simple combinations. You can do interesting things with a model that you can fit on one page. All right, stop there. Any questions? That definitely sounds like lunch.
I think it was one of the Pack's paper on the simple model.
Yep.
Did you suggest that one up there?
Yeah, it would have.
It would have, yeah.
Yeah, it would have been me. Yeah.
Because in that model, it wasn't applied to instead of soil, litter, and photosynthesis. It was instead of like predator-prey dynamics.
Okay.
Or something like that.
So he probably has one of those as well.
Okay. It looked very similar.
Yeah. And roughly the same things will apply.
Yeah.
It's really surprising how those simple dynamics will look quite similar.
Yeah, absolutely. Yep.
So predator-prey dynamics was the classic form for making these simple chaotic systems. That's when, so for a while, after Lorentz built the first chaotic model of the weather in the mid-1950s, there was a quest for how simple could you make a model that actually had chaos. And it turned out that the simplest forms looked like predator-prey models. And now they think they see ecosystems that actually do this, where the system crashes out and you can't get it back. And that's because of the coupling terms between predators and prey. So it's not at all surprising that Mike applied that model to a different system.
I thought it was also really interesting how you were saying about using optimization term for a model.
Yep.
Yeah, I didn't know that.
Ah, okay. So that's. I mean, we'll be doing that probably by the end of your project.
Yeah.
We'd expect to be trying to improve using these formal techniques the way Cable handles C13. That'll be kind of the. If we get there, we've done well.
That's ambitious. Though. It's like some sort of like water efficiency term.
Yep.
That'd be ambitious.
Yeah,
but I'm up for it.
But as soon as you model C13 in Cable, you have those terms in there anyway.
Yeah.
So then the question is just whether you have enough data to actually constrain them.
Yeah.
And that's, you don't know until you do it. You often find that I'm a poor predictor in these complicated models of knowing whether the data is actually going to elucidate one of the parameters you care about or whether it's not.
Yeah.
As we'll see tomorrow, actually.
I guess it depends on also what region you're in. Like in Australia, potentially it would be much more useful.
Yeah, that's right. So carbon 13 probably has uses in Australia and in the tropics that it doesn't have in the Northern Hemisphere, where plants are basically drowning.
Yeah. Great talk, though. Great talk. I really enjoyed it.
Hey there. Ah, cool. Now, I need to see Robin because she stole my adapter this morning. Actually, she didn't steal it. I gave it to her. Yeah, you did. But I really did that. Okay. Yes.
Two things I have to say. So Jeremy's just copying And we're talking though about, he's giving me both the MATLAB and Python files.
Yep.
Yep. The other thing is we do have somebody coming, I can't remember, from the Marvel Virtual Marine Lab to do an introduction to the students at the beginning of the lab.
Cool.
So that'll
Yeah,
be able to
my lab is probably more like an hour and a half than full time. So there's no anything. If people finish early, they finish early. I'm quite relaxed about that. So yeah, take as much time as they need.
So I think they said half hour max.
Sure.
And so we'll do that and then we'll transition.
Go for it. Yeah, no problem.
We can have a break sometime in the other and
Yeah.
biscuits. And then when we're all done,
Yeah.
people can go to the interface.
Absolutely fine. Do you remember where I handed an adapter across to Robin this morning? We were testing whether my adapter would work for her machine. Is it still there?
No, but Robin's still there. I'll just go ask her.
Right.
All right.
The adapter? I have Peter's adapter. Yeah. But my adapter has been lost in the ether of this room. Boo!
Did mine work for you?
It did. Can I borrow it?
Yeah, keep it.
Can I keep it? And if I
You can keep it on a finite. You can rent it. I mean, for free.
for tomorrow morning.
Yeah, that's fine.
Yeah.
No worries.
Like if I forget to give it back to you,
I know you
I
live.
know where you're.
Yeah. Oh, it's hard work. I'm tired.
So that's the bug.
Cool. Drop this. Now, if you take that key and just think, yep. Nice one to wait till this one. Always die. I don't know how people do 3 hours.
That was good. That was good. Yeah. But even though I've played it before.
Yeah.
But yeah.
You're probably the second.
Yeah.
The second one was good.
I think it's the tracks which are more exciting. Yeah.
But that had to be done. There's going to be all the options. Let's get outside. See what the temperature's like. Ooh. All right.